Okay, in our previous video, we started talking about dynamics. We introduced the idea of forces. We then moved on to talk a little bit about Newton's three laws. We did a couple of examples there, and toward the end of the video, we talked about Newton's third law of motion, symmetry and forces. And so I'm going to do a little bit of an example here where we might apply some of those ideas, and then we're going to move on to talk about normal forces, right? Okay, so let's start off with this example, and let's keep in the back of our minds here that we're going to be making use of Newton's third law, the symmetry and forces. So the question goes like this. And this is a question from the text. This is number 10 from chapter 4. Okay, so a motorcycle is traveling at 90 kilometers per hour. It then accelerates at 3.5 meters per second squared. The total friction opposing the motion of the motorcycle plus rider system is 400 newtons. And the mass of the motorcycle plus rider is 245 kilograms. We want to know what the magnitude of the force the motorcycle exerts backward on the ground to provide this acceleration is. Okay? And so I'm going to start out by just drawing a little bit of a picture here. What do we have? We have our, let's call this our motorcycle. It's going to have a mass of m. It's going to be accelerating in this direction. So there's going to be some force which is providing that acceleration, and we know there's some friction, some force of friction countering that acceleration, right? And so we have some numbers that we can put to this. We know that our acceleration is going to be 3.5 meters per second squared. We know that the force of friction has a magnitude of 400 newtons. We know that our mass, well, the mass of the system, the motorcycle plus rider, is 245 kilograms. And now we want to be a little bit careful, right? So we're talking about well, what we want is the magnitude of the force that the motorcycle exerts on the ground backward. So we want the force that the motorcycle is exerting on the ground backward here. So there's some force being exerted on the ground by the motorcycle. So this is motorcycle on ground, right? But the force that's actually accelerating us is the force of the ground on the motorcycle. Newton's third law tells us that the force of the motorcycle on the ground is just going to be equal to the negative of the force of the ground on the motorcycle. So we can just think of these as having the same magnitude. Well, they will have the same magnitude. They'll just have opposite signs, right? So we can kind of ignore this idea of motorcycle on ground and just worry about the force of the ground on the motorcycle, and then the force exerted backward will simply be the negative of the force exerted by the ground on the motorcycle, right? So let's just proceed calculating the force that the ground is applying to the motorcycle, and then we'll just slap a minus sign on it, and that'll be the force of the motorcycle on the ground. Okay? And so let's start off here by translating our initial drawing into a free body diagram. So the free body diagram here will be pretty simple. It'll just look like this point. We're going to have our force here, and it doesn't matter which one it is. It'll be ground on motorcycle, but in the end, we're just going to be changing it to motorcycle on ground, and we have friction in the opposite direction, right? So what does this tell us? Well, then we have Newton's second law. So Newton's second law tells us F equals ma, right? Or in vector form like this. And so what is this going to do for us? Well, we're going to then think about the net forces. We can get that from our free body diagram here. We're going to total up the net force, and we're going to see what we get. So let's take a look here. We have F net equals mass times acceleration, but this is just equal to f. We're going to call that our positive direction, so we're kind of setting up a positive x axis in this direction. So we're going to call f as though, well, we're going to label f as though it's pointing in the positive direction, so it's going to be f minus the force of friction here. And so we can rearrange this stuff here to give us f equals ma plus lowercase f, our force of friction. And then it's really just a matter of substituting in numbers. So f is going to be equal to, well, we have the mass, that's 245, times the acceleration, that's 3.5, plus our 400 newtons. And if we were to add that up, we would find that our f is equal to 1257.5 newtons. Okay, and since we're only interested in the magnitude of the force that the motorcycle exerts backward on the ground, well, this is the answer, right? So if we were interested in the direction, we'd pick up an additional minus sign, but the magnitude is just the absolute value of that, and so f has the same magnitude pointing in opposite directions depending on whether we're talking about motorcycle on ground or ground on motorcycle. But since we're only interested in the magnitude, that's our answer right there. Okay. And so this is just one way that we need to keep in the back of our minds that the direction of the force, well, that the motorcycle is applying a force to the ground and the ground is applying one to the motorcycle, and we need to keep in mind that they're balanced, they're equal in magnitude, but they're opposite in direction, right? And we have our magnitude right there. Okay, so really, all the examples that we're going to be talking about in this chapter and even the next chapter all only involve applying this one equation, F equals ma, right? So just Newton's second law over and over again in different forms. Now, just because we're only using that one equation doesn't mean that all the problems are easy, right? We have to be careful how we manipulate these situations and how we apply Newton's second law to get at our answers here. So basically, it's all just going to be an exercise in practicing how to use Newton's second law here. So I'm going to introduce normal force here. We've already talked about normal force before when we were talking about the difference between masses and weights of objects. And so we can just quickly read through this here. So gravity is a pervasive force that acts on all objects at all times. But in spite of this, we often see objects sitting on the Earth's surface with no vertical acceleration, right? Gravity is acting on an object sitting on the surface of the Earth, but it's not accelerating into the ground, right? So there must be some force countering the force of gravity, and this is the force of the ground pushing back up against whatever that object is. We call this force the normal force, and the normal force is always perpendicular to the surface that's providing that normal force, okay? And so on flat ground, well, we see no acceleration in the y direction here, right? Our ay is equal to 0, so there must be no net force in that direction, and that's because the normal force perfectly counterbalances the force of gravity, right? So that's what happens on flat ground. But what would happen if we were on an incline, right? And that's what we're going to look at now. We're going to look at an example where we have a mass on an incline, and we're going to take a look at sort of what happens there, okay? And so this is example 4.5 from the text, and we're dealing with a skier of mass 60 kilograms on a slope that makes an angle of 25 degrees with the horizontal, and we want to know what her acceleration is if the friction opposing her motion is first 0, so there's no friction opposing her motion, and then second, let's say there was a friction of 45 newtons opposing her motion, right? So I'm going to start off by drawing out a little picture of what we have going on here. I'm going to draw it kind of big so we can work with it. So we can imagine this is our slope. This is flat ground, right? I'm going to label this. Do I have a picture here? I do. Okay, so we're going to call this theta. We're going to have our skier here. Oh, I'm sorry. So we have our skier here, and actually let me turn off that ringer so that doesn't happen again. Okay, so we have our skier here. Our skier is of mass m. We're going to have some force of gravity, which is always going to be perpendicular to the ground, right? So this is our force of gravity acting in that direction. We're going to have some normal force, and as we mentioned before, the normal force is always going to be perpendicular to the surface, right? So it's perpendicular to our surface here, and this is our normal force. And we can put some numbers to some of this. We know that our mass is 60 kilograms. We know that our angle theta here is 25 degrees. And so there's going to be some acceleration in this direction, right down the hill, not into the hill, like digging into the ground, and not lifting off up above the hill, but right along the surface of the hill. So we want to know what this acceleration is, and so that's kind of the problem here. This is a setup for the problem. So generally speaking, we've always dealt with these problems thinking about things in the x and y direction, right? So we want to break things up into an x and y direction here, and usually we would probably think to maybe break things up like this, right? Maybe we would do an x in this direction and a y in that direction. But we're going to see that that's not a great choice here, because we already have the normal force pointing kind of a little bit y and a little bit x, and our acceleration is a little bit x and a little bit y. So maybe the correct choice, well, not maybe, but actually the correct choice is going to end up being tilting our coordinates slightly and solving the problem with a tilted coordinate system. So what we want to do is we want to break up the problem so that we have things either perpendicular to our hill, or no, sorry, parallel to our hill, or perpendicular to the hill. Okay? So this is going to be the two coordinates that we're going to choose. So we set up a coordinate system like this. I'll draw it over here. This will be the components of our vectors that are perpendicular to the hill, and these will be those that are parallel. Okay? So let's erase this over here. And the first thing that we're going to want to do is we're going to want to break up this force of gravity, or what we sometimes call weight, into its components that are perpendicular with the hill and those that are parallel with the hill. So let's think about what we have going on here. We have, and I'm going to draw it again over here maybe. So we have our slope here. We have our mass, and we have, I'm only going to draw in the force of gravity here. Okay. But we want to break this up into perpendicular and parallel components. So how is this going to look? We can imagine that we want some part of our gravity pointing in this direction, oops, and some part pointing in this direction. This will be what we call the part of the force of gravity that's pointing perpendicular to the hill. It's pointing into our incline. And this part will be the force of gravity parallel, and this is what's sort of pointing downward along the hill. We can see that these are all vectors, and if we were to add up this one and this one, our perpendicular and our parallel components, they would add up to give us the total force of gravity, right, if we added them tail to head, and that's exactly what we want. Okay? So what we really need is we need this angle in here. I'm going to call this angle alpha. And let's remember that this angle here, this is what we called theta. So now we need to find, and let's remember this is a right angle in here, even though it doesn't look like it from what I've drawn. We need to find what alpha is, right? Well, there's a lot of pretty simple ways to find alpha. Let's also remember that this is a right angle in here. But if we know what theta is, and we're given theta here, and we know this is a 90-degree angle in here, this angle in here, then we know that because every triangle has 180 degrees, and we know that we have a right angle in here, let's call this angle up on top here phi. We know that that theta plus phi plus 90 equals 180, right? Because we know that all the angles in the triangle have to add up to give us a total of 180. We can then subtract 90 from either side, and this means that phi must be 90 minus theta, right? And we also know that this has to be a right angle, right? But then if phi is 90 minus theta and phi plus alpha has to be equal to 90, right? We can see that because right in here we have alpha and we have phi, and they add up to 90. If that's the case, then we can simply substitute in phi and alpha into our 90 degrees up here. And maybe this is going to get a little bit sort of messier on the page here, but I'll clean it up afterward. We're going to end up with phi equals phi plus alpha minus theta. We can subtract phi from either side, move the theta over to the other side, and theta is just equal to alpha. So this is just sort of one way to get at this angle. Another way would be through similar triangles, or however else you can convince yourself. But in the end, we're going to find that this angle in here, this alpha is just equal to theta. Okay? And if we know that, then using all the tools that we developed before to break up vectors, we can break our force of gravity up into its horizontal and its, well, not horizontal and vertical here, but parallel and perpendicular components, right? And so let's take a look at that. Maybe I will draw it over here. So if we have a vector like this, and we call this our force of gravity, and then we have a vector here which we call FG perpendicular and FG parallel, then we can see, again, if this is theta, we can see by the same arguments we developed before that FG perpendicular is just going to be FG cos theta, and FG parallel is just going to be FG sine theta. And you can sort of go through the whole trig argument here using this mnemonic here, right? But it's the same thing that we did before for breaking up the vectors, right? And so this is what we're going to need to use. So let's keep these equations in mind as we break up our drawing here. And I'm going to redraw it down here again with our force of gravity now broken up into its components, right? And so what do we have? Again, we have our slope. I'm going to call this theta. We have our mass here, and I'm drawing theta much larger here. It doesn't really matter. This is our mass. We're going to have some acceleration in this direction, and we know we're talking about a coordinate system that goes like this, where this is parallel and this is perpendicular. So we're going to have our normal force pointing in this direction. We're going to have some, and I didn't draw it on the previous version, I guess I can draw it up here. We're going to have some force of friction opposing our motion. Either it'll be zero or it'll be non-zero, as in the case of part B. But so we're going to have some friction opposing our motion, and now we've broken up the force of gravity, so we're going to have some part of the force of gravity which we call FG parallel pulling this thing down the hill, and we're also going to have some component of our force of gravity which we've called FG perpendicular pulling this thing into the mountain, okay, like against our normal force here, okay? And so if we then we're then going to draw our free body diagram, it would look something like this. And I'll keep it sort of tilted like this just to keep things sort of obvious, right? So we have our friction operating in this direction, our parallel force of gravity operating in this direction. We have our normal force in this direction, and our perpendicular force of gravity operating in this direction. Excuse me. And so maybe I'll put this in here. Okay. So now let's take a look, as we normally would. We're going to break things up into their components that are in the two opposite directions, right? Or in the two orthogonal directions, I should say. And so let's take a look at what's going on in the parallel direction, right? All we're really interested in for right now is the acceleration of this thing down the hill, and we know that the acceleration is operating in the parallel direction here, right? It's operating in this direction. And so let's take a look at what's happening in the parallel direction. So we can take a look at F net in the parallel direction, and this is going to be equal to mass times the acceleration in the parallel direction. Well, what do we have going on in the parallel direction? Well, we have the force of gravity in the parallel direction, and opposing that in the opposite direction, we have our force of friction, right? So what is the acceleration going to be? Well, right away from this equation here, we can generate an equation for what that's going to be. We're going to end up with the acceleration in the parallel direction, and that's what this is over here. That's going to be equal to the force of gravity in that parallel direction minus the force of friction acting against us, or against the motion in that direction, divided by the mass, right? And so this is really the equation that's going to guide us to our final answers. We can make one substitution, though. We saw that the force of gravity in the parallel direction can just be rewritten as we have up here, right? Rewritten as Fg sine theta. And so let's do that. It's just going to be Fg sine theta minus lowercase f over m. Okay, and so that this equation will lead us to our answers in, or maybe I have enough space here. This will lead us to our answers here at the end of the page. And so what do we have going on? We need the force of gravity on this object. Well, we know that the force of gravity and the weight are the same thing, right? And we know that those are just mg, right? So Fg is just going to be equal to mg, right? The mass times our gravitational acceleration. And so this is going to tell us that A is equal to mg sine theta minus f over m, right? And so we could clean this up a little bit, but basically in the end, all we're going to be doing is substituting in numbers, and maybe I will do the last step of cleanup here. We're going to say this is g sine theta. This is just dividing out by the m, right? Okay, and now it's just a matter of substituting in numbers. So this is our formula, and for part A, we want to know what the acceleration would be if the force of friction opposing motion was 0. So we would just set f to 0. So f goes to 0, and this tells us that the acceleration in the parallel direction is going to be equal to g sine theta, and at this point you would just substitute a number. So you would substitute 9.8 for g, and your theta is 25 degrees. If you did that, you would find that you had an acceleration of 4.14 meters per second squared. That's for part A. And in part B, F is going to go to 45 newtons. And if you substitute that in, you're going to end up with F over m. It's going to be an additional term there that you're going to subtract, and you're going to end up with acceleration in the parallel direction equal to 3.39 meters per second squared. Okay, and so those would be the answers for part A and B, and this is sort of how we're always going to handle these problems with sort of ramps and stuff in a way where we want to we want to choose a coordinate system that's convenient for us to work with the problem. We're always looking for coordinate systems that make our problems easier, and here the choice of coordinate system that makes this problem easier is choosing the parallel and perpendicular directions. Okay.